to half stick, that looks good. And when we go to full high pitch, the bubbles are just locked in place. So that's what we want to see. We want to see the bubbles perfectly level and not move as we go from half stick to full stick and from full stick all the way down to low stick. With collective throw set, we can start to set cyclic throw. And we want to position the swash plate in the aft and right corner. But first of all, let's just check the direction. If I go right, I've got right cyclic. If I go left, I've got left cyclic. If I give aft cyclic, the swash plate tilts forward. So that's backwards. So again, in the CCPM menu, all that I have to do is select elevator and run that from plus 60% to minus 60%. Let me make that change. And with minus 60% set, aft cyclic gives aft movement of the swash plate, and my cyclic controls are correct. Now let me change shots. We're going to deflect the swash plate aft and right and check the clearance between the swash plate and the main shaft. With this shot, you're looking from the forward left side of the helicopter up into the swash plate. And again, the swash plate is deflected to the aft right corner. What you need to do is just look and make sure that when you lower the collective pitch, that the swash plate comes down and fits over the collar. Now, for maximum cyclic response, the swash plate would just almost touch that collar, and it looks pretty close right there. So I'm not going to change anything. I'm just going to leave it the way it is because, again, it looks good. If you had a different type of helicopter and the swash plate was farther away from the collar, you would simply increase the aileron and the elevator percentages equally in the CCPM or the swash mix menu. The transmitter stick is still rubber banded to the aft and right 45-degree position, so that's the way the swash plate is tilted. Now what we want to do is check the low limit, so I'm going to come to full low stick and we're going to see how close the swash plate comes to the top of the bearing block. Ooh, and that is really close. We're looking at maybe, what, a half of a millimeter there. I probably won't change anything, but if you wanted to maximize negative and positive throw, you'd adjust all three push rods, maybe a half a turn, one full turn, to bring the swash plate right down to the top of the bearing block, and then you'd have maximum travel at the top of the swash plate throw. With the collective and cyclic set, we have a few miscellaneous tasks to do before we punch the Botita numbers back into the normal pitch curve. The first is we want to make sure that the washout arms are perfectly level at half stick. So again, make sure half stick is set and eyeball these level. These look very nice. If they're not level, adjust these links until they are. Next, we want to make sure that the mixer arms are level. The flybar birdcage kind of obstructs the view here, but basically this ball link should be level with the rod, and of course this screw is level with the rod. And then if the mixer arm is not level, just adjust this push rod first, and then come back and adjust this push rod to keep 12 degrees of pitch at full stick. Now, as I was going through this, I noticed that this mixer arm is really incorrectly positioned according to the instructions, and this is the way it's assembled according to the instructions. But really, to keep the rule of 90 degrees, this mixer arm should really be flipped so that instead of drooping down a little bit, it should slope up a little bit, which will keep the angle 90 degrees to this push rod. Now, it's not that big of a deal practically, but if you want to make things really, really right, go ahead and flip this so that it angles up a little bit. Now, when you do that, the reinforcing rib will go toward the inside, and you'll have to grind off a little bit of that reinforcing rib so that it clears the flybar carrier screw on the inside. So you can do what you want to do, but I just thought I'd point that out to you. Let's check the freedom of movement in the washout arms, the mixer arms, and the ball links. And we do this by just rotating the head at full low pitch and full high pitch. It's a two-step process. First we'll do it with the swash plate level, and then we'll do it with the swash plate deflected aft and 45 degrees. So here's full high stick, and again, any modern helicopter really isn't going to have any problem with the swash plate level. Here's full low stick, and that looks good. Now let's go on to the real test, and that's with the swash plate deflected to the aft and right 45 degree position. Okay, here I'm picking up a little binding, and that's with this ball link right on the bottom reinforcement of the blade grip. I showed you how to trim this reinforcement down a little bit to eliminate the binding. I haven't done it in this helicopter because after the DVD I'm going to flip the pitch arm from the trailing edge to the leading edge, so I'll end up sanding what is now the top of the blade grip. Okay, and that looks pretty good. I've also ground with a little sanding drum in this mixer arm area. I've ground off the little reinforcement rib because this push rod lays right in there in the mixer area. And let's go to full high stick. Same thing, I've got some binding here. But everything else looks pretty good. So basically in the T-Rex, if you grind away a little here and a little in the blade grip, you'll have perfectly free movement, and you can use these same principles and apply them to any other helicopter. You won't run into this unless you're doing radical 3D, but I wanted to point it out to you nonetheless. Here's 0 degrees main rotor pitch, and if you go to full negative pitch and then put in some right and forward cyclic, if this servo arm isn't trimmed off, it can come down and contact the top of the main gear. So to preclude any chance of that doing that, I've taken a sanding drum, chucked it up in a Mototool, and just sanded a little trough in the rib of the main gear. Here's a head-on view of the swash plate, and now I want to physically adjust the length of the push rods so that the swash plate is just tilted just barely perceptibly to the right about like that. Basically, I'll start out by shortening this one full turn and lengthening this push rod 1 full turn. Here's a 1 turn adjustment in each push rod. We've got a barely perceptible right tilt in the swash plate, and when we hover the helicopter, if it needs any right or left cyclic trim, we'll do that by adjusting these 2 push rods. Finally, you want to check all of the push rods and make sure the threaded area on the one end is equal to the threaded area on the other end. In other words, you don't want one ball link screwed on all the way and the other ball link almost ready to fall off. So after you've made all these checks, then you can go ahead and punch the Botita numbers back into the normal pitch curve. As we start the tail rotor and gyro setup, first of all we have to figure out which way the push rod has to move to give right tail rotor. Or you could use left, I'm going to use right. So for right tail rotor, the tail rotor has to go this way, which will blow more wind to the right, which will push the tail to the left, which will push the nose of the helicopter to the right. So to give right tail rotor, the push rod has to move forward. Now let's go ahead and move forward to the servo. From my previous shots of trimming the servo arm, I just randomly stuck the tail rotor arm on the servo, and you can see that it's all out of whack. So what I have to do is pull off the tail rotor servo arm and get it as close as I can to perpendicular 90 degrees. Let me go ahead and do that. Here you can see how the top of the servo arm is back a little bit too far, and if I rotate it forward 1 spline, now it's forward a little bit too far. So it looks like I'll have to rotate the servo arm 180 degrees and then whack off this excess length of servo arm right here. It looks like this is as close as I'm going to get to a perfect 90-degree angle between the push rod and the servo arm. You cannot use rudder sub trim to adjust this angle, because if you use rudder sub trim, that's like putting a control input into the heading hold gyro. So let me transfer the ball and screw it into this hole. I've screwed in the screw for the tail rotor servo arm, and you can see that the tail rotor linkage comes into the servo arm at a beautiful 90-degree angle. Now let's see which way the servo arm goes. When I give right tail rotor, I'm looking for the arm to go forward. So I give right tail rotor and the arm goes back. So I need to go into the reverse menu and reverse the rudder so that now when I give right tail rotor, the top of the arm goes forward. Okay, that's good. Now let's go ahead and set the tail rotor pitch. Now you can see that the tail rotor is angled like this. What we want to do is change the tail rotor so it's angled about like this, and we do that simply by taking two pliers and putting one on either side of the tail rotor push rod, and then just shortening the tail rotor push rod so that we have something like that. That's going to be close. Again, we'll fine-tune this when we lift off the helicopter and hover with the gyro in the rate mode. This is a top view of the tail rotor gearbox, and here's an even better way to set tail rotor pitch. Just go ahead and set the bell crank 90 degrees to the standoff. Now let's see if the gyro works the right way or the wrong way. Again, right tail rotor moves forward, so when I yaw the helicopter to the left, the initial movement of the tail rotor servo arm ought to be forward. And here we go. Okay, the initial movement is aft to the rear, so the gyro works backwards. Let me go ahead and reverse the direction of the gyro. Here are these itty-bitty little pots. The top one sets the reverse of the gyro. That's the one we want to move. The bottom one, when the switch is to the left, it's for a high-speed digital servo. When the switch is to the right, it's for a normal servo. And here's the limit pot. We want to make sure the limit pot is wide open because we'll set the pirouette rate by where the push rod is in or out on the tail rotor servo. So to reverse the direction of the gyro, all that I have to do is move the top switch over to the right. Let's see what we've got. With a left yaw, the tail rotor servo arm ought to move forward. And it does. So now our tail rotor stick input is correct and the gyro is working properly. While I've used JR's 500T gyro and 3400G servo for my installation in the T-Rex, Futaba also has a great combination, and that's the GY401 gyro along with the S9650 servo. Now, the 401 gyro is fractionally lighter than the 500T, but the S9650 servo is fractionally heavier than the JR 3400G, so it's basically a wash. The other option is to install an E-flite sub-micro heading lock gyro, and this is a really nice unit. It's installed on my son's T-Rex 450. The setup for any of these units is exactly as I've described with the JR 500T and 3400G combination. Am I a good enough pilot to push any of these units to their limits? Absolutely not. In preparations for autos, we need to trim the tail rotor to flat pitch, and the way we do that is just snap on the throttle hold switch and then just beep the tail rotor trim until the tail rotor blades are at 0 degrees or flat pitch, and that looks pretty good. Now, if we adjust the tail rotor during the initial hovering checks, this 0 degree position may change, so we'll double check it before we do autos. Because the DX6 does not have dedicated trims for throttle hold, when we enter an auto rotation, the tail rotor is going to hold the hover pitch setting. And again, you can look at the DX7 and you'll be able to see how we set up the DX7. I'm not actually going to fly the DX6, so this is why I want to give you that warning. So for instance, if you do a hovering auto rotation and the helicopter is at 3 feet and you flip on the throttle hold switch, the nose is going to yaw about 30 to 45 degrees to the right as the helicopter comes down. Now, you can compensate for that by giving a little bit of left tail rotor if you want to, but I find that giving left tail rotor and increasing collective pitch can get a little tricky. So normally when I do a hovering auto with the DX6, I just flip the throttle hold, add the collective pitch, and let the helicopter yaw to the right 30 or 45 degrees. Now, when you do auto rotations from altitude, the yaw isn't as noticeable. The helicopter will yaw about 10 degrees to the right, but then as the tail rotor slows down in the auto rotation, the yaw will come out, or the nose will stay straight. So basically, from halfway down in the auto rotation through the flare and the touchdown will be exactly the same as in the DX7. With the gyro adjustments completed, I can mount the receiver to the front of the plate. I've used a little piece of Ace foam tape here. This will bump right up against the gyro, and I'll go ahead and remove the backing and stick the receiver down. For additional security, I've added 2 small rubber bands around the receiver. Now I'm going to screw in the servo arm screw, and then in preparation for the powered runs, do a nice detailed pre-flight over the whole machine. With the setup of the helicopter essentially complete, let's go ahead and mount the battery and do some rotor blade tracking checks. Go ahead and plug the leads from the ESC back into the motor. All fine tracking changes are made by adjusting this link a half a turn at a time. If you shorten this link, you'll reduce the blade pitch, and if you lengthen this link, you'll increase the blade pitch. Here's the black tipped blade, and here's the white tipped blade. Let's take a look at the blade tracking. Now it looks like the black blade is a little high or the white blade is a little low. Because we used the white blade as the master blade, let me go ahead and bring down the black blade a half a turn on the long link that goes from the swash plate up to the mixer arm, and we'll see what we get. With the black blade pitch lowered half a turn, let's take a look and see what we get. And that looks beautiful. We're good to fly. Now I've intentionally tracked the black blade high, and I want to show you what that looks like. I adjusted the short pushrod linkage 1 full turn. Here we go. With this light background, you can see that the white tipped blade looks short and the black tipped blade looks long. And again, I don't want to go up to full power or hover power when the blades are out of track this far, but I just wanted to show you what it looks like. Before I fly, I want to go through the entire transmitter menu to make sure everything is right. We're starting out at dual rate and expo. And here we go. That's aileron, that looks good. Elevator 30%, rudder linear, that's good. Auto dual rate, that's all inhibited. Reversing switches, they're set. Sub trim, that's set. Travel adjust, that's set. Swash mix, aileron and elevator 60%, and pitch minus 64%. And most important, exponential inhibited. That looks good. Throttle hold, we'll adjust that at the field. That'll end up somewhere between -5 and -10%. And the switch is rudder dual rate, that's good. Okay, throttle curve for normal, we have low, and then 33% at quarter stick, 49% at half stick, hovering at 65 for an upright hover, and 100%, that's good. Exponential is off. Stunt curve, low stick, 88%, then 70% at the inverted hover, 72.5, 75% for the upright hover, and 88% for the full power climb out with Expo off. That looks good. Stunt curve 2 will be just a little bit higher, 88 at low stick, that's the same, but here we're a little higher, 75, 77.5, 80%, and the full power climb out at 88%, and the exponential is off. Pitch curve for normal, 34 is -2.5 degrees of pitch. That's good. Same thing at a quarter stick. Half stick, 0 degrees pitch. The upright hover at 68%, which is 5 degrees pitch. And the full power climb out at 10 degrees pitch. Expo is off. Pitch curve, stunt 1, -10 degrees of pitch. And 23 is -5 for an inverted hover. 0 degrees, upright hover at 68, plus 5 degrees of pitch. And the full power climb out at 91% with Expo off. The same thing for stunt 2, 0, 23, 45, 68, and 91, Expo off. That's good. Okay, for pitch curve for throttle hold, we have 23, that's -5 degrees of pitch. Then we're running a linear line up to 68%, which is plus 5 degrees of pitch, and 100%, plus 12 degrees of pitch at full stick for autos. And the Expo is off. That looks good. Revo mix, everything must be 0, and it is. The gyro sense, okay, heading hold is 0, position 0, 75. The rate mode, position 1, 25. And that's all assigned properly. We have rate for the normal flight mode, heading hold for stunt, and rate mode for auto rotations in hold. That's good. Okay, program mix, aileron to throttle 25%, elevator to throttle 25%, rudder to throttle 5%, that all looks good. The countdown timer 9 minutes. And the servo monitor, nothing to that. And we've rolled all the way around. We're back at the dual rate and Expo menu, and everything looks good. Training gear. If you're learning how to fly an electric helicopter without the benefit of a simulator, you'll certainly want some type of training gear. These are 2 suggestions or 2 recommendations that I would give you. First of all, this is just a 1/4 inch birch dowel from your local Home Depot or Lowe's. Just cut it in half. It doesn't quite come out to be 24 inches, it's about 22 inches. Then visit your Big 5 or local sporting goods store, get some practice wiffle golf balls, and then just use O-rings to hold them on the ends. The wiffle balls should spin so the helicopter can skate on the ground. Use little zip ties to zip tie the helicopter to the training gear, and make sure that the main shaft is centered exactly over the center of the training gear. The other option is to use a carbon fiber training gear. This is carbon fiber from Midwest Products. It's 1/8 inch diameter tubing, and I've used the same wiffle balls on the end. I've used a little piece of fuel line with a washer, and a washer on the other side, and a little piece of fuel line. Again, all the balls roll, and the training gear will skate around on the ground very nicely. This training gear is a little bit lighter, a little bit stronger, but again, the birch dowel is cheaper, so go ahead and take your pick, just that you use something if you're learning to fly without a simulator. Everything's been checked and double-checked, and we're ready to fly. There's only one problem. It's dark outside. Well, on the other hand, I could fly under the street light. I've done it before. But the video footage wouldn't be very good. So I'll tell you what, we'll wait 12 hours for the sun to come up, and I'll see you then. It's a beautiful day. We've got a helicopter that's never been flown. Let's go ahead and start to trim it out. Before we fly, I want to do a range check. Now, Horizon says that we ought to get 30 paces or 90 feet with the bind button pushed in on the back of the transmitter. On my other T-Rex, I got substantially less than that, more like 12 to 15 paces. So let's see what this machine does. I do need to disconnect the motor before we do this because the main way that I'm going to see if the radio is working is by moving collective pitch. So, okay, we are T-Rex DVD, that's good. Everything's low, let's power up. And I'm just going to face the helicopter so it points toward the radio. That puts the two little antennae 90 degrees to the incoming radio signal. Okay, there's 30 paces, and the collective pitch is working just fine. Now let's see what I get when I push in the bind button. Yeah, nothing. It's dead. The bind button is out, and we've got full control. So let me push in the bind button and just walk in until things start to come alive. And there it's alive. So let me just count the paces. Okay, 21 or 20.